Good afternoon, everyone. I am Veeramuthuvel. So, thank you for inviting me to be part of this event. Thank you for all the introduction. I'll be covering two parts. One is the Indian space program, what we have done so far, and then I was a project director for Chandrayaan 3. So I thought I'll bring some slides and uh, tell up, tell all of you that how we achieved the soft landing onto the moon surface. So we started the Indian space program. Basically, Dr. Vikram Sarabhai, he has told that we should be second to none in the applications of advanced technologies to the real problems of man and society. So we started the space-based technologies for the benefit of common man. That is how the program started with the visionary of Dr. Vikram Sarabhai. And we begin this space era by launching tiny rockets from the Tumba Equatorial Rocket Launching Station, which is near to the Trivandrum, where we used sounding rockets to launch in the middle atmosphere and the atmospheric region to study various purposes like meteorological studies and various science experiments. And that is how the first ISRO has formed in 1972, and also the DOS also, 69 ISRO was formed, and 1972 DOS Department of Space was formed, and ISRO was brought under the Department of Space. And we had various rockets in the beginning. As I told, we had sounding rockets, basically to take it to middle atmosphere and then ionosphere, where we had a very little tiny payloads which can be used for scientific purpose. Then the first launch vehicle which has actually gone to the space, till that point of time we had orbital suborbital flight. The SLV-3 was the first launch vehicle which has taken to the space, where we had our Dr. APJ Abdul Kalam was the project director for this mission, and we became the fourth country to have our own launch vehicle to carry the payloads into the space. So we had something like 35 kg of the payload, which is taken to low Earth orbit, and successfully we launched on 18 July 1980. Then after that, we started with the ASLV program with the little improvement in the payload weight from 35 kg to 115 kg. And all the way, we have actually had, after the several experimental launch vehicles, we had a operational launch vehicles, where we all know that PSLV, Polar Satellite Launch Vehicle, then geosynchronous launch vehicle, and then LVM-3. The LVM-3 is the heaviest launch vehicle what we have till now. So PSLV can take the spacecraft mass of nearly 1,700 kg to the SSPO. We call it as Sun Synchronous Polar Orbit, which is actually very significant, because the sun angle with respect to the satellite and the Earth will remain constant, which is used for various remote sensing purpose and various Earth observational studies. And also, the PSLV is a versatile vehicle which can take the spacecraft to the sub GTO orbits also, with the mass of nearly 1,400 kg. And you can see on the bottom of the slide, where we have nearly 320 tons of the total vehicle weight. And GSLV is the next launch vehicle, where it can take the spacecraft to the low Earth orbit as well as to GTO. GTO means geosynchronous transfer orbit, with the mass of 6,000 kg in LEO, and with the GTO of 2,200 kg. And then we elevated with the bigger launch vehicle called LVM-3, which can take nearly 2 times of the GSLV, where 4,400 kg of the spacecraft can be taken to the GTO. And also, we felt there is a need of a small satellite launch vehicle, because this launch vehicle will meet various requirements from the startups and then the private industries, and the space ecosystem is growing, where we can take something like 400 kg of payload. So that's how that SSLV, small satellite launch vehicle, has come. This is how we have an operational launch vehicles which is available with ISRO as of now. And coming to the satellite systems also, satellite systems, we launched various satellites right from Aryabhatta, Bhaskara, and Apple. And we have different applications, like we started with INSAT series for weather and communication purpose, and also GSAT series for entirely for specifically for communication purpose. Then ResourceSat series of satellites is basically for natural resource management and various applications, like we had optical as well as medium resolution types of scientific instruments. And Cartosat is something cartographic applications for urban planning, where we had optical payloads like panchromatic type of instruments we had, and also it is meant for high resolution images. And OceanSat, it's mainly meant for oceanographic studies, and RISAT, and recently we launched NISR, that is NASA ISRO synthetic aperture radar, where this is a synthetic aperture radar. The bigger advantage is it can image in the night time also, whereas all these visible bands can image only in the daytime. And you can see on the right side of the screen where we started microwave payloads from scatterometer with the 50-kilometer resolution to nearly 20 meters, 3 to 20 meters kind of a resolution. Over the period of last 30 years, we have actually advanced that microwave payload. Now, also we have recently the NSR satellite, which I was mentioning. We had S-band payload, S-band synthetic aperture radar, whereas NASA has realized L-band synthetic aperture radar. And both the payloads, it's a dual payload, which was launched using our launch vehicle and mainly meant for both NASA and ISRO. And optical payloads also, we have grown from panchromatic camera from 1 kilometer resolution to nearly sub-meter kind of a resolution. You can see the 1 kilometer to 0.28 meter resolution. Recently, we launched Cartosat 3 satellite. That is a third generation satellite with a resolution of 0.28 meter kind of a resolution. And similar way for the hyperspectral also, we moved from LEO to GEO. We are under various stages of development. The hyperspectral payload is as a distinct advantage where we can have multiple bands, whereas the panchromatic is having a single band, whereas multispectral has some few bands like 4 bands or 6 bands, whereas in the hyperspectral you can have many number of bands. The spectral resolution also is very important for different applications. Similar way for the communication, we started with the conventional transponders with the C, extended C band, S band, and KU band. Now we have moved to high throughput satellite like Ka band and KU band, where we can have a spot beam coverage with the high resolution, high data rate capabilities. And similar way for navigation, right now we are lagging here. We have taken this navigation payloads for a regional coverage for our own Indian landmass, but also we have a future plans of taking it to the global coverage, like how GPS and GLONASS and BDU, all these things are there. Likewise, we also have a plans, but not in near future. Maybe another 5 to 10 years time, we have that plans. But now with the recent navigation satellites, we have L1 band in addition to L5 and S band. And as I was telling, the satellite technology also has moved from various matured stage to a very, very advanced stage. We also have an aspiration of taking the payload from not only from the low Earth orbit, even from the geosynchronous orbit we wanted to image. One of the biggest advantages in one shot from the geosynchronous orbit, if the satellite can image, the entire India can be covered in one shot. So that is the biggest advantage. For that, we have to have, it is a trade-off between the satellite mass and the launch vehicle capability what you have, and the payload size which can be carried. That is the biggest limitations, but with the technology we can overcome. We are working out like a deployable kind of a telescope, where in the space it can be deployed or it can be assembled in the space. Like we conducted recently the docking experiments, where one object and another second object can come and dock each other at the orbit in the space. Due to the limitations in the volume, mass in the launch vehicle, this can be overcome by assembling in the space. So that kind of plans we have. But the ultimate aim is from the geo orbit, whether we can improve the resolution to a 0.1 meter kind of a resolution. So it gives like a temporal resolution also. Whereas in the LEO orbit, what it happens is it goes around the Earth every 90 minutes, and 14 times it goes around the Earth. And we have a limited time it can image over the India. Whereas if you look at it from geo orbit, since the orbit is well synchronized with respect to the Earth's rotational speed, so always it can be stagnant from one point of wherever you launch, whichever the point you are above the Earth, so constantly it will image. And we are also working on the single platform with both microwave and optical payloads. Whereas now if you see, the optical payload is one category and microwave payload is another category. How to bring together so that the data fusion will happen? Because as I told, the microwave has some features, whereas optical payloads has some features. So how to combine both the things? And I was mentioning about the deployable structures, then the hyperspectral will go into a very detail, like as I told, the number of bands will be more, the spectral bands, since the spectral bands are more, you will get more features and more applications. So for that we are working out with the resolution of 1 meter. This is a very very tall task, but already we are working on this field also. And then geo based SAR, whatever I talked about, the SAR is all LEO. Again, we wanted to take it from geo. And Navic global coverage, which I told, our own navigation constellation with the global coverage, like how GPS we are having. On orbit servicing in LEO and GEO. This is one of the very important thing which we are working. Like for example, our satellite life, how we have got life, satellite also has got a life. That life is dictated basically on the propellant, what it has, or the battery capacity, how many discharge and charge cycles it is undergoing. So the propellant is one of the very important thing to maintain the life. So how do we service that propellant? Like for example, the one of the biggest challenge what we have is here, we can access some of the device and then we can repair it, whereas in the space that is not possible. The once you launch, the satellite life is predetermined before the launch. So how do we service it? Like the docking is important. You dock it and transfer the propellant from one module to another module, so that you extend the mission life. So that is called a servicing mission. And then lunar navigation and communication. See, we have now many programs beyond the Earth, like going to the moon, going to Mars, but we need a navigation and communication. Like navigation, I can actually I can come to this venue by putting a Google map, and then I can reach, navigate myself. Whereas to go to the moon, go to the Mars, we are depending on constantly the on orbit determination using the Doppler principle. Whereas how do we get this navigation, self-sufficient navigation, so that the craft can move from one place to another place? So this requires a navigation as well as the relay communication. Because now what happens, if you if you want to launch a satellite to the Mars, you know the Mars, how far it is from the Earth. Because of the distance, it takes more time, like something like 40 minutes, the maximum it takes one way communication. The time you communicate, 40 minutes it takes the radio signals to receive to reach the satellite. Similar way, the satellite communicates to Earth, it takes another 40 minutes. So we cannot do a meaningful operation. For that, we need a relay communication. So we are working on that as well. And moving on to the space science and exploration missions, as you all know that we had a lunar program. First, we launched Chandrayaan-1. Basically, it was around the moon. It was orbiting around the moon, where we have some payloads which will actually sense from the distance. We had, for our credit, we have discovered the water molecules from this Chandrayaan-1. That is how the thirst of going to the moon again began. Even though NASA, using an Apollo program, launched very very long back in 1969, but the water molecule is available in the moon was found by Chandrayaan-1 with a payload of both NASA and ISRO, called a moon mineralogy mapper, which has actually told us the water molecules is available. Second one is the Chandrayaan-2 with the ambition of enhancing this resolution of the payloads. We had more sophisticated payloads. We had two objectives. One is the orbiting around the moon, other one is landing onto the moon surface. See, however you are away from the surface, you cannot exactly tell whether whatever the experiments we are carrying out, it is correct or not. To confirm that, we have to go to the surface and then really see that whether it is correct or not. So for that, we had a landing objective. As you all know that landing we could not accomplished successfully during Chandrayaan-2 time, whereas the orbiter is still going on. Even though our mission life was 1 year, we launched 2019, but still it is ongoing. And we had a very very, as I told, very high resolution payloads. One of the payload was 32 centimeter resolution, which is the best available globally. And Chandrayaan-3, in order to meet that landing objective and roving objective, we have taken up this Chandrayaan-3. And Chandrayaan-3 was a very successful mission where we had a lander and rover also. And we had many scientific payloads, which I'm going to talk about in the subsequent slides. And not only the lunar missions, we had Mars and solar missions as well. This is something, a Mars orbiter mission, which was launched 2014. And in our first attempt, we have successfully acquired the Mars planet. You know, the Mars is very far, and we have to go into a heliocentric phase. And every planet has got its own sphere of influence, and you have to properly maneuver and capture that Mars planet, which is a very, very difficult task. And with all this, the communication delays we have to manage, which means we have to build all the autonomous intelligence in the onboard to take its own decision, real-time decisions. So it was in the first attempt we were successful in this Mars orbiter mission, and it worked up to 2022. And Aditya L1 mission was a recent mission, which is actually first time we have gone to the Lagrangian point, which is the point where the gravitational force is nullified between the Earth and the Sun. So this point was used for constantly looking at the Sun and see to measure various parameters like coronal mass ejection and various solar flares, and which is actually a concern to our Earth. And as well, other scientific missions like astrosat and exposat. Astrosat is a very, very successful mission to ISRO, and it has given terabytes of data to the scientific community. Basically, it has a multi-wavelength astronomical observatory, and we had many data which is actually given to not only to India and even worldwide. Every scientist have used this data. And exposat is the recent launch in 2024. This is again a X-ray astronomy satellite with the spectroscopy and polarization measurements, which is also very successful, but this data is yet to be released because it is recently launched. And right now, the space infrastructure, if I talk about our ISRO Indian space infrastructure, so far we have launched 135 satellites. And currently, 56 satellites are operational, and remaining satellites are missioned. The mission life was completed, and these are the satellites which are all available, serving for various purposes. Like you can see on the left side, the Earth communication satellites, for high throughput satellites, DTH point of view, and multi-beam S-band satellites. On the right side, you can see the Earth observation satellites. We have 22 number of Earth observation satellites. Navigation satellites, we have 8 number of satellites, and space exploration 4, and technology demonstration like SPADX, which I was talking about, docking experiments, we had 4 satellites. And coming to applications, what for we launched the satellites? It is mainly meant for the, as I told in the first slide, it is for the common man to really give the to the benefit to the society. So we have 5 verticals. One is the Earth observation for agricultural purpose, environmental monitoring, and resource management, crop estimation, oceanography studies, then cartographic studies, and potential fishing zone using the oceanography satellite. And SATCOM applications also. We have, initially we started with telecommunication, broadcasting, then slowly we moved to the societal applications like telemedicine, teleeducation, and search and rescue, and radio networking, rural connectivity, and serving to the underdeserved regions, and so on. And NAVIC applications also. Right now, the NAVIC applications, we don't have the global coverage. We are also trying to establish 3 more satellites to cover the Indian landmass. And in addition to that, some of the atomic clocks, we have a setbacks. So those satellites, we are using it for other purposes, like you would have come across the real-time train tracking. All these informations are coming through this satellite with the combination of communication payload and the navigation chips, where we can use this satellite for the real-time train tracking. Similar way, we are putting some of the transmitters on the shipping terminals to see that any type of distress is happening, the fisherman will get a notice such a thing is happening, so he can move to the safer zone. And disaster warning and management, where various satellites are used, like cyclonic warming, flood damage assessment, and flood risk zone, and then forest fire and risk mapping. And also the strategic applications. The strategic applications is something I cannot talk about, but this audience is very important. So safety and security of India, where we have many satellites, and we have a very active program. Since it is classified and highly secret, I won't be able to tell what we are working on it. And this is some of the infrastructure, glimpses of some of the infrastructure, where launchpad, you can see our SDSC Sriharikota, where we have 2 launch pads. We primarily use it for launching our low Earth orbit and geosynchronous orbit satellites. And this is one of the very important facility at IPRC, where the cryogenic engine developments and semi-cryogenic technologies are getting developed there, and electric propulsion system facility and satellite building. Say it is in Bangalore, we have our URSC satellite center, where the satellite building and testing facility is there. And also we have for deep space network, we have 32-meter antenna that is also near to Bangalore called Bailalu, where we have a 32-meter antenna is one of the facility where we have many antennas at various locations. Like we have master control facility at Hassan, and we have ISRO that is in Bangalore for basically to control and monitor the low Earth orbit satellites. And also we have payload data reception at Hyderabad NRSC, and also we have a space application center at Ahmedabad. We have set of antennas there also. And if you can see the accomplishments of ISRO at a glance, so we had, to our credit, totally 238 missions. We had both launch vehicle and satellites, and also we have 2 suborbital flights by startup accomplished. And now if you see the number of satellite missions are, it's going to go exponentially. And in fact, last 10 years comparison, you see the satellites and launch vehicles, we had many. It has increased drastically. And some of the world records also ISRO has made. Totally, we have something now, 9, we were the number one. One is the Chandrayaan 1, where we had the water molecules on the moon. Then second one is the Mars orbiter mission. First time in the first attempt, we have captured the Mars planet. And then 104 satellites in one mission. That is PSLV C-37 in 2017, we have launched all 104 satellites in one go. And then Chandrayaan 2, I was mentioning about the 32 centimeter resolution, where it can actually image 32 centimeter, which is the lowest resolution which we have at present. The next resolution is 50 centimeters from LRO, from NASA. And Chandrayaan 3, first time we have gone to the high latitude of the south pole of the moon. We were the first country to do so. And S200 solid motor with only 2 static tests, we have qualified the LVM3. And also the cryogenic stage development. If you see 3 world records it has given, even though we were using initially from Russia, but once the technology was denied, we had to make indigenously. And the present chairman was the project director to develop this cryogenic technology. And now moving on to my next topic is the journey of Chandrayaan 3. We had a lot of challenges, struggles, and then finally we also could accomplish successfully. So the landing missions, we had so many players are there. One is USA, Russia, China, and India. So USA first initially they started with the Ranger landers, but largely it was unsuccessful. Then they deployed Surveyor, and Apollo was actually the crewed mission. And USSR also has got a Luna program. They had various Luna missions, Luna 1 till now recently, before Chandrayaan 3, there was a failure. And then China also has a Changi mission. They started with Changi 1, Changi 2. Basically, it was a orbiting mission. Then Changi 3 and 4 was a landing mission. Then they had a Changi 5 and 6 as well. Then India also has got a Chandrayaan mission. And you can see that green color, we were the actual one to go near to the South Pole. And Chandrayaan 2 flight performance, what has happened to the Chandrayaan 2? We should know. Basically, we were successful. The launch was successful. It was orbiting around the moon. But when it comes to landing, you can see there are 2 curves here. One is the red color curve and another one is the blue color dotted one. So the red one was expected on the day, whereas the blue dotted one was achieved on the day. You can see the first phase was successful. That is called rough braking phase. We call it as a rough braking phase. In order to give an analogy, you just imagine we have to start with the 0 speed from Sriharikota, and we have to achieve nearly 11 km per second. 11 km per second speed, and we have to go all the way to the moon, and which is 4 lakh kilometers away, and we have to reduce the speed to 2.4 km per second, and finally at 30 km from the lunar surface, the speed will be around 1.68 km per second. That is 1683 meter per second. From that speed, we have to come to 0 meter per second for a soft landing within something like 19 minutes to 20 minutes autonomously. That is a major task. That means navigation, guidance, control, everything has to work unison, and all the decision has to be taken autonomously with the real time without any ground intervention. It has to happen. And since the moon does not have atmosphere, it is full of vacuum. So we have to decelerate using the active propulsion system. Otherwise, if like Earth, like atmosphere is there, we can deploy parachutes which can decelerate the speed and then it can reduce the speed. Since in the absence of that, we have to do this. So the first phase went well. The second phase, which is called as a camera coasting phase, we got a lot of deviations. Just to give simpler terms, the craft is rotated opposite to reduce the speed. So we are firing the engine in an opposite direction to reduce the speed. Now what has happened, we have actually reduced to a greater extent, which is beyond 3 sigma, and we lost the altitude, and we have to reach to the same destination because the target point is it's fixed before the launch. So since the target point is fixed and you have reduced the velocity, in that process the guidance demanded a bigger maneuver. When it was maneuvering almost 360 degree, it rotated. When it is rotating, it fired in an opposite direction. Finally, we lost the altitude. We ended up with high residual velocity. It is something like 50 meter per second. We had a velocity in the horizontal direction and vertical direction, which is beyond the lander leg capability. So it got crashed, and all the parts, it has come as a parts because it was not a safe landing. This is what the Chandrayaan 2. Then we started with the Chandrayaan 3. We learnt from our mistake. And first of all, Chandrayaan 3 was entirely indigenously made. The rocket is built by India. The satellite is developed by India, launched by India. We have not dependent on anyone. So all the systems was indigenously developed, and we had several scientific instruments in lander, rover, as well as on the propulsion module as well. And we had one tiny rover which weighs around 25 kg, and also it has got all the autonomous features. And the various mission elements I talked about: propulsion module, lander module, and rover. The main purpose of the propulsion module is to carry the lander all the way to the moon and detach the lander and rover, and it has to land. And upon landing, the rover has to come out from the lander and it has to row around the moon surface and deploy some scientific instruments and transfer the data back to the Earth. That was the overall objective. And we had various mission milestones, like 14 July 2023 we launched, and 31st July we had a translunar injection. Translunar injection means that is the day where we actually go out of the Earth. And then LOI, 5th August was LOI, that is called lunar orbit insertion. That is the day where we captured the moon, or in other words, the satellite around the moon. And then PM and LM separation was happened on 17th August. That is nothing but the propulsion module and lander got separated. And after that, the lander will be on its own way. And the 23rd August was landing onto the moon. And we used JPL NASA as well as the ESA stations also. This is the ground station which we have to use. Even they launch and they also use our workstation, our ground stations, because geographically apart the stations are required, because once the satellite goes out of the Earth, you have to communicate constantly, 24/7 you have to communicate. Because of the geometry, the Earth is spinning and the moon is going around the Earth every 28 days. Because of that geometrical differences, sometimes the satellite will not be visible to the Earth, to the India. So we need to hire the stations which is opposite to geographically 180 degree opposite. We may require the similar thing. US and ESA also may require. And this is the power design phase, where we had various phases: rough braking phase, attitude, roll phase. And this is something we actually designed before the launch, before the landing. And various phases were there and the milestones were defined. And after this is defined, we exactly got on the day what we got on the day. I'll just tell. This is what we designed. Then various enhancement we did in the lander's robustness compared to the Chandrayaan 2. The one of the thing is the touchdown limit we have increased. The touchdown limit in the sense, the lander leg was capable enough in Chandrayaan 2 was only 2 meter per second in vertical direction, 0.5 meter per second in horizontal direction, beyond which the lander leg cannot survive. Or in other words, it will topple. The stability cannot be assured, or the strength cannot be assured. So in Chandrayaan 3, we gone ahead with the 3 meter per second and 1 meter per second. Even though it is 1 meter per second is the delta increase, but in terms of kinetic energy, if you see half mv square, so v square times the energy has to be increased. So we necessarily put so many dampers to enhance that velocity. And also we had one very, very important sensor called laser Doppler velocimeter. This laser Doppler velocimeter, which is totally new, which will give 3-axis velocity information. I was mentioning that GPS, in the absence of GPS in moon, we have to have a terrain relative navigation sensor, which means I don't have the state vectors. For a state vector means I need x, y, z direction, that is position, and velocity called x dot, y dot, z dot. All the 6 important parameters are required for me to navigate and land onto the correct point. Because I should know where I am. If I know where I am, I can navigate where I have to go. So for that, in the absence of GPS, I have to have a terrain relative navigation sensor. So we used a called navigation laser Doppler velocimeter. Basically, it works on the Doppler principle. Even though this instrument initially we thought we will procure from NASA, and we budgeted something like 53 crores, and the total budget was 250 crores. The entire budget was 250 crores. In that, this sensor alone was 53 crores we have factored. Because of COVID, and because we had lot of budget shortage, and we have developed indigenously, and we gone ahead with our own sensor. So ultimately, the entire sensors also we indigenously developed, and this sensor we did not procure, and we saved something like 30 crores. And various other improvements we made in terms of algorithm, thrust, angle continuity, and the landing area also. The bottom one you can see, the landing area we have increased. Earlier in Chandrayaan 2 was 500 meter by 500 meter size. And we have increased the Chandrayaan 2 area to 4 kilometer by 2.4 kilometer, because we wanted to very sure that this time we wanted to successfully land. So you know, even in Earth, you cannot get that kind of a flat surface. You will have you go anywhere in the Earth, you will not get that kind of a flat surface. But same is the case in the moon also. The moon has got a big craters and boulders we cannot get. So but we have used effectively the Chandrayaan 2 OHRC data, which I was mentioning about 0.32 meter resolution, that is 32 centimeter resolution. That image was very well utilized, and those images we have thoroughly characterized for this 4 kilometer by 2.4 kilometer. These images were a priori stored in the onboard in Chandrayaan 3 lander, and that was used to compare at just before the landing. If you see, if you would have watched that landing, when it was just above 100 meter surface, the craft was hovering. Hovering is nothing but constantly it is in the same position. You know, the moon also has got a gravitational force. Even though it is not equivalent to Earth, it is 1/6 of Earth's gravitational force, which is nearly 1.65 meter per second square. But in order to constantly hover, you have to have an upward force, and that upward force supposed to be the variable force, because the propellant is keep on getting depleted, and you have a variable downward force, that is m into g, and you need to have an upward variable force to compensate that kind of a gravitational force, and it has to remain in same position without having horizontal velocity, without having vertical velocity. For that, we used the engines, throttleable engines. First time we developed the throttleable engine, not a steady state engine. And during that time, one camera was operated, and it used to take an image just below the lander, whether any craters and boulders are there, whether it is conducive to land. Otherwise, you know, in the car also we have a ground clearance. If you have a very big just a stone in front of the car, it cannot navigate. Similar way, we have certain ground clearance below the lander as well. So this image, this camera will take an image, it will compare with respect to the onboard image, and it has to compare and take decision within 22 seconds. In the 22 seconds, it has to retarget as well. So all this intelligence we have built in that lander. And some of the simulations and tests, we got a confidence based on the simulations and tests. Otherwise, it is impossible to have a successful landing. So one of the biggest challenges what we faced is the kind of a test creating the moon environment in Earth. As I told, the gravitational force is different, and moon doesn't have an atmosphere. We cannot create vacuum, but we employed different methods. Second is, at the time of landing, the entire mission life is only 14 Earth days, which is equivalent to 1 lunar day. Because in the absence of nuclear resource, we had to have, we need to depend on the solar power. So for that, exactly the starting of the lunar day, we have to land. And 14 days only is the mission life. We need to landing on the starting of that lunar day, which is the sun will be elevated with about some 6-degree elevation from the lunar surface. So similar time we have to carry out this test. So we created lunar craters and boulders near our Chitradurga, where we created all the landing areas, prepared that area, and we flew all these sensors in the helicopter. And through this, all the sensors were characterized. Whatever the sensors I was talking about, laser Doppler velocimeter, cameras, and we need to create the actual illumination condition, because for that we used to conduct the test exactly between 6:15 to 6:30 in the morning. So we had many challenges. When we have to conduct this test, we have to start our campaign in the midnight around 12 o'clock. So what happens is, exactly the pilot has to take, and he has to go to that site, and between 6:15 to 6:30 we have to complete this test. Most of the time what happens is, weather condition will not be conducive. Sometimes the pilot will not hover there. Sometimes the wind will be more where we cannot hover, and all are working. Sometimes the sensor may not work. We had many challenges. We overcome many things, but we have successfully completed this test. And another test is very important test is the drop test. You can see a test bed, which is a lunar simulant soil test bed. What we did is, we know that lunar soil has got some anorthosite properties. So we saw in near to Salem, where we got this rock which has an anorthosite property. We pulverized into various grades of soil, and we made test bed out of it. And we created a flat bed as well as a slopey bed, because we do not know exactly the lunar condition, whether it is going to be flat or it is going to be slopey, or we are going to have the flat terrain, soft terrain or a hard terrain, or we are going to have boulders, craters. We created all types of combinations, and we dropped over some height. So we need to ensure the strength is offered and necessary stability is there, because the lander should not topple. The topple can happen with the horizontal velocity or in a slopey terrain. So all such things we have simulated, all sort of different touchdown conditions we have simulated, and we qualified that. And finally, the landing performance summary. You can see on the table, where we supposed to go minus 69.37 degree latitude, that is South Pole, and 32.31 degree east longitude. And we were well within 170 meter accuracy in the along range and 300 meter accuracy in the across range. That is the kind of precision we achieved. Just 170 meter from, like going to the South Pole from 4 lakh kilometers away. Just this is the kind of achievement. Even though we had 4 kilometer by 2.4 kilometer, I was telling, but in the meters level we have achieved. And this is where you can see the star mark where the lander landed exactly on near to the South Pole. And some of the images also we captured from the Chandrayaan 2 orbiter, which is orbiting around the moon at 100 kilometers distance. And the lander the orbiter has taken the photograph of the lander after the landing. You can see one small dot. This is a kind of a dot you can see, that is called lander. And also it is confirmed from other images also, that is LRO image from NASA as well as KPLO image. And upon the landing, you would have seen this video. The rover ramp will get deployed, and the rover will come on only on that time, and the rover will roll out from the ramp, and it will always communicate with the lander, because rover has got a very tiny system. It cannot actually directly communicate with Earth. Now you can see the actual visuals from the onboard camera. Earlier was a simulated image. The rover has come out of the lander. The lander has taken the picture from the rover, and we saw that video. And you can see the rover has taken the picture of lander on the left side. And when the rover was coming out, we had our ISRO logo on one side, and Ashoka Chakra on the right side of the wheel, and also our Indian map on the rover. This was a very important moment for us at that time. And there are some multiple payloads we had in the lander. It is not only the landing objective is an important thing, because that is a starting point for us. Any mission, if you want to have an in situ resources monitoring or management, you have to have a landing technology. That is one of the very important thing. Upon landing, we conducted several experiments for the 14 days. One is the ground vibrations and seismicity experiment, where we dropped one payload. You can see here in this, I'm just moving the cursor, where it is called ILSA. This is called Instrument for Lunar Seismic Activity, where we drop this instrument, and it will always be in contact with the surface of the moon. So any sort of vibration, because of no atmosphere, the many craters will come and many meteoroids will come and impact the lunar surface. That's how the craters are formed. Whereas here also in earth also many things are coming, but because of the atmosphere and because of the speed in which it is coming, it gets burnt. So there even that natural impact point we wanted to measure using an eye vibration accelerometers, which we carried in this instrument. We got, for our credit, we got some natural vibration also, and even the artificial also. When the rover is moving, because of the ground vibrations, it will sense. Similar way, one of the probe we had, that probe was inserted into the lunar regolith for about 80 mm, and every 10 mm we had one temperature sensor, where we wanted to measure the temperature and thermal conductivity of the lunar regolith, to see that how the temperature variation is there from the surface to the towards the regolith. Because this is of importance, because future, if you want to settle there, if you want to have a human colonization, how the temperature is going to behave, how the soil is having the thermal conductivity, this is of very important. And for us, we have seen that the temperature was 60 degrees centigrade at the surface, and as we go deep and deep, it went to minus 10 degrees centigrade. So that kind of a strong vertical gradient we could see. Then another one of the very important experiment we found was near surface plasma experiment. Near surface plasma in the sense, so how much of electron density over time it is varying, because this is of very importance. We use RF waves. Like for example, I was talking about some of the sensors which measures the height information. This, we use a radio wave frequency. This radio wave frequency, we have seen, as you come closer to the surface, the signal is becoming feeble, the signal is getting dropped. So this kind of information we got through this experiment. And rover also has got two important experiment, where we wanted to measure the surface chemical composition of the surface. So there are various minerals like iron, iron, chromium, and magnesium, silica. There are various minerals it has measured, and we used two different principles. One is laser based induced spectroscopy, and another one is we used a curium 244 radio isotopes. Through lighting that surface, we measured the chemical composition. And this is something a rover path planning. The rover has been moved almost 100 meters. It is a very tiny rover, and it has to navigate. It cannot navigate a bigger crater or boulder, because it's a very, very tiny rover. And with all these 14 days, 24/7, we have moved the rover and maximized the payload operations. And some of the experiments, whatever I told orally, it is just put in the graph form. And moving on to our space vision, just put it in one slide, where we have very, very active challenges in front of us. One is the launch vehicle. If you see, we have LVM-3, but beyond that, we are working on next generation launch vehicle for crew landing onto the moon, where we require a very, very big launch vehicle. And similar way, we wanted to take it up beyond Earth missions like Gaganyaan. We are going to have a crewed mission, and also we are going to have our own space station called Bharatiya Antarakshi Space Station. That is by 2035 we are aiming. On the bottom side, you can see various experiments like Chandrayaan-3 we have done. Now we are going to have Chandrayaan-4 and Chandrayaan-5, where Chandrayaan-4 is going to be a sample return mission. And also further missions. Finally, it will take us to Indian landing onto the moon by 2040. That is our target. And beyond 2040 also, we have many constantly sustaining, like how we can go to space. How the tourism is there. Similar way, we can go to moon and come back beyond 2040, like a space tourism. And we have to have a constant human presence on the moon beyond 2040. Like we will have shuttles from Earth to moon and moon to landing. Such plans are also we are working out. Thank you for your attention. Thank you. If you have any questions, I can take up, or I can wrap up.
There are so many, like moon is different, Earth is different. There are so many variations, right? Like even in the testing phase, you mentioned there are so many creation that you have to do to simulate the environment. How do you manage the error margin?
See, the error is that is why we have selected 4 kilometer by 2.4 kilometer. Even with with that size also, we wanted to launch. We wanted to land. So there are various instruments which can give error, like right from launch till landing. So the various instruments are coming and participating. Like launch vehicle will have some error, and the propulsion module taking the lander will have some error. The lander landing will have some error. So three components we can split. All these three components we will take it, and we will work out 3 sigma. And this time in Chandrayaan 3 we have taken all, not in RSS sense, we have taken additive sense. Like say that day all are going unfavorably, like all are taking into positive sense, all are taking into negative sense. That is positive, all parameters are positive, all parameters are negative. If you account additively also, we wanted to land. That was our approach. With all that, we have to ensure for that it comes with the more propellant, but we carried this time. But that day it was actually a nominal landing, just a nominal. How we say it is a textbook landing, I can say it is a textbook landing. But we prepared for a bigger error, but we got only 170 meter. If you see the norm, it was around 120 meters is the error ellipse we got.
First of all, it's an honor to be, attending your session and listening to it. I think it's really fantastic, and thank you so much for that.
Thank you.
We as citizens are really, really proud that ISRO has been able to raise the flag, country's flag, on the moon. My question here was, what is the message you would like to give us as a group in terms of the learnings of Chandrayaan 2 into 3? What are the top 3 or 4 learnings or takeaways that kind of helped us to get Chandrayaan 3 to where it is right now?
Thank you. So one of our team learning was basically learning from the mistake, and resilience is one of the very important thing. I can take. I will tell that is a takeaway for our team, the resilience. And second is there is nothing like luck. We have to do the correct things. If you do the correct things, correct thing will happen. So we have to do. There is no substitute for that. So we have to do the correctly. The correct things will happen. These are the two things we did, and we were always constantly working. Even though many difference of opinion among the teams were there, like we have Chandrayaan 3 is like various types of engineers, various types of scientists, various types of the technicians, and down the level if you see the contract people, there are various people contributed to the mission. With all the difference of opinion, the common goal was to land. So when it comes to that, the common objective, so everybody worked. So the teamwork also is a very important thing. Individually nobody is great, but when the team is aligned, when the team is actually working for a common objective, then it will be a successful.
Pleasure to have you, sir.
Thank you.
Very important question, I feel, coming from the cybersecurity team. When we talk about Chandrayaan 2 or 3, I know that there are so many other countries who are also having the same target towards the lunar surface today. So were you facing any kind of cyber issues with Chandrayaan 2 or 3, which you can disclose at this platform? Because we know that everybody is interested with the data, what we are doing on the research, on what are the tests we are doing, on how we are achieving it, what are the important aspects. So more or less, any country today, they are interested with us, especially after the Chandrayaan 2, everybody is interested. So any challenges which you faced, which you can share with us?
No, many things I cannot share here because it is all very classified things. See, what I all shared is only unclassified things, which is available in public domain. But one important thing I can say, there are many things going on. You all know about it. So one of the thing is the interference what we get from the satellites, from various advisories. So how do we overcome that? So we have, for example, the telecommand, we have a CDMA kind of a receiver where we can actually strengthen this area. Similar way for the telemetry as well, we have encryptions, various types of encryptions. So we are working right now with the 128-bit encryption, now 256-bit encryption, AES encryption. This is a standard available, but we have our own ISRO encryption. And also now for some of our missions, we also getting a SAC certified encryptions. There are many things which I cannot disclose now.
Thank you, sir. And whom do you think we are challenging with?
No,
Which country we are challenging
No,
with?
there is no
No,
competition for us. Actually, we have our own goals. You have seen that
Thank you.
the moon mission is not to compete with anybody. It is, you have seen our target. Like we wanted to see that moon as a stepping stone for reaching to another planet. Like moon is very close by. At least we can go from moon can be treated as a gateway to go to Mars. That's how other countries are also planning. But it is not only that is a goal for us. There are various verticals you have seen: earth observation, communication, navigation. It is for our own common man, so benefit to the common man. That is our goal.
Thank you so much, sir.